I have two questions. Do you have any reason to use linear actuator for the motion?
Sorry?
Do you have any reason to use linear actuators for the actuation?
I mean, one of the reasons, really, the start of the project was we were looking for something different from harmonic drives. Because we have now more, six or seven talos in the world, and few blobs made the robot jump, and few of them broke torque sensor, broke harmonic drive. When you hit a mechanical limit with an harmonic drive, you can basically twist the flex spline, and harmonic drive are super expensive, super difficult to replace, and also the torque sensor are quite expensive. We were looking for something more robust, and imagine the actuator of the bigger one that we have is about 5.2 kilonewton peak force, but the ball screw can resist 15 kilonewton.
15.
Yeah, and that compared to an harmonic drive is like 10 times more. Then, in terms of efficiency, harmonic drive, at least in our experience, is about 70% efficient. Then if you add all the transmission and bearing and cross floor and so on, you end up with a system that is maybe 50–55% efficient. Ball screw by itself, the component is 96% efficient. And especially depends on the lead that you choose. If the lead is large enough, the system is very transparent.
And could you explain the required torque of the knee joint?
We didn't care about the knee torque in this case, because when we started sizing the system, we thought only about the vertical force that we were needing for making the robot jump. And this is physics. 40 kilograms, 30 centimeters, you need a takeoff velocity of 2.4 meters per second, and that also translates directly to an acceleration at the let's say, vertical speed. And that basically, again, by design, the system can stand and can accelerate fast enough so that it can reach this 2.4 meters per second at the takeoff time. And that, if you then do the math, it translates to a joint torque at the knee that can be up to 450 or 500 Newton meter. But again, we don't have actuators there. Everything is kept there by the constraint of the closed kinematic chain. What we get here is that the actuator, the linear actuator in the femur, can generate this 5,200 Newton here. Then that are mapped to the vertical force here, are reduced by a factor of between 4 and 5 depending on the configuration, because it's non linear. So it means that here we can have a vertical push of about 100 kilograms.
I think you undersold this idea of using the 4-bar linkages, because you said you wanted to produce vertical force, but you also snuck in this thing that you're now able to have an actuator up here to produce torque at the ankle, and you hid that from us.
Yep.
So, is there a reason you didn't consider using mechanical compliance in your foot or somewhere else in the structure? It seems like it would solve some of the problems that we've been talking about here.
Yeah, actually we have no experience with elastic, let's say, component, especially the experience that I've seen in humanoids using, humanoid robot in the legs using elastic transmission were not so successful so far, even because maybe it's complicated to deal with them. You need to tune the spring stiffness in the right way. We are actually in contact. There are many possible customers of the Kangaroo that they actually would like to extend the platform, adding springs in some points of the structure. We are open to suggestion. Or actually, one of the strengths of our company is that we do everything in-house, from electronic to mechanics. So we had no experience in that, so we prefer to go with the stiff, rigid system, and then extend it if it's needed, and if someone knows how to do it. Over there.
Do you mind going back to the slide where you did the kinematic design? It looks like a 2D plot.
This one?
Yeah. Can you explain a little bit about the knee? It looks sort of like an inverted 4-bar. I'm not entirely sure what's going on there. may be too long for.
So there are two 4-bar linkages here, the orange one and the blue one, light blue one, yeah. And the actuator of the knee, the actuator inside the femur is actually pushing and pulling with this red bar the tibia. So if we disconnect the two 4-bar linkages, you will have a traditional linear actuator to actuating the knee that you have seen. Maybe I don't know if Nadia or I don't know who, maybe Tesla bought something similar. Adding those two closed kinematic chain actually basically constrain the angle of the pitch of the femur to the motion of the tibia. And that also has another benefit, that basically, normally if you have a serial robot with individual rotary joint at the hip, knee and ankle, when you just want to lift the foot, you are actually using part of the speed and the torque of the pitch actuator only for contracting the leg, and actually normally the motors of the hip and the ankle are activated in the opposite direction of the knee, because you have a triangle, the sum of the angle is 180 degrees, so you need to make that constraint. So actually it's like in a typical robot, the three motors need to satisfy a closed kinematic constraint in order to have a vertical lift of the foot along the vertical. And here we implemented that mechanically. So the passive joints implement this constraint so that here you have a perfect triangle. That was the trick. And this basically also relieves the need for a very powerful pitch hip actuator only for lifting the leg. So the pitch actuator now is only responsible for moving back and forth the foot, but is not responsible for lifting it and making it move down quickly. That also is one of the reasons why most of the time when you have the toe off, it's the limitation on the speed, or that there is very high requirements on the maximum speed of those joints just for having a very fast push off of the ankle. And this also basically, it's let's say at the end it's like in our case kangaroo, we can think about it like it's a Cartesian leg, in which the leg length is responsible only for the distance of the foot to the hip. The ankle are actually responsible for the orientation of the foot to respect the ground, and then you have the other three joints basically are placing the leg on a sphere centered around the hip. So it's the coupling, like a Cartesian decoupling of the actuation of the leg.
Plus 2.
Plus 3.
So I would have a question regarding the distance between the legs. It's quite broad. I think it's 260 millimeters or something. Is there any reason?
Space for fitting everything?
Yeah, but
Normally that is one of the criteria.
Because from walking, it feels like the unilateral constraint forces might be increased, because if you're always bouncing to the other side, so in case of running,
Yeah.
it feels like.
Sorry, so you mean the distance between the two legs is quite tight?
Yeah, so I would narrow the distance so I would narrow the step width when walking or running. And this is what, it looks really wide.
Yeah, so you have, the question is that this seems to be quite wide.
Is there a real reason behind, or is it just?
Because the reason behind that, we wanted to keep as much as possible vertical the force propagation on the bar linkage, especially for the ankle, and also because in terms of construction, it's easier. the load distribution in this case it's easier. But it's true that we are also thinking about shaping the tibia or the femur like in a curved way, so that actually we can have a more I don't know, like a human. Also, the femur have an inclination, so the knees are closer than the hips. For the moment, it was the easier thing to manufacture, because you can imagine how complicated it could be to manufacture, build, and manufacture complex aluminum pieces in a bended way. And also in this case, to reduce the cost and the weight, the tibia is a carbon fiber tube, very cheap, very easy to replace, and there is no electronics from here down, so also the cabling is quite reduced and more robust.
Can the feet touch?
Yeah, the feet can touch. Actually, one of the main reasons also with this one of the main, let's say, claim or complaint about Talos is that the feet were too close. At least it's very easy to get self-collision with Talos when you want to walk on a line, or you want to have, and also for the hip. So basically, we try to move a little bit away the hips, but also reducing as much as possible self-collision of the feet in camera.
I don't know. That was the second one. There was one more.
So you touched on something that I wanted to ask. So for example, in terms of going for more agile and non or even terrain, would you think this design is going to be helpful? Because you have now jumping on planar terrain, which was the initial design. Do you think this can help you, or you need to adapt the design for those kind of non-structured environments?
I mean, we are optimizing nowadays because also we are trying to actually build. We started looking at some co-design, like how to choose the right parameters for the mechatronics so that it can be successfully used by the control. So use control in the loop when you design the robot. And this is also, thanks now to the data that we are gathering with the system, are helping understanding if the pipeline of control, design, simulation, and build it's sound. And at the same time, we think that for doing very agile motion, you need an upper body. You need you need at least simple arms that enable to generate angular momentum or recover in complex, more complex, let's say, scenario when with the legs you cannot do that much, especially in the air. When you jump with this system, you cannot do that much. You wait for the landing.
And then part of the same, you mentioned one of the problems with Talos, you cannot put like walk on a line. Can this design do it?
Yes.
As it is right now?
Yeah.
So
with a final question. So the ball screw is good for generating a large force, but it's not that drivable. So it's not easy to achieve compliance utilizing force observation. How did you achieve compliance?
The leg length is very, very, very drivable. If the leg can fall.
Repeat the question so we can understand.
With the ball screw, saying that it's easy to generate high forces, but it's not that easy to implement a transparent transmission, so a drivable system. What we have figured out here is that for the leg length, the transmission is very transparent, especially because of the components selection. Depends on the lead most of the time. So if you have, at the end is the same, the lead translates directly to the gear ratio of the system. So if you have a larger lead, lower gear ratio, the system is transparent. In our case, even if the leg is very lightweight, because I think that from the leg length actuator down is less than 4 kilograms, and the system falls down nicely when it's powered off. And actually this is helping us actually to consider reducing directly the number of load cells in the system. But it's true that for the smaller leads, the friction or the back drivability is not as good. And that also basically at the end is a trade-off between the geometry of the closed bar linkages and the lead of the ball screw to reach the right trade-off in terms of back drivability and power.
Can I ask a question to the questioner? Maybe don't answer it here, but it's kind of an act of, there's a religious belief in this transparency and back drivability. And maybe now's not the right time to have the discussion exactly, but I don't really understand where that comes from.
But yeah, he showed some compliant motion during the video, so yeah.
You don't do it now, but it's somehow people, it's just people say it has to be there, I don't understand that.